Welcome to this comprehensive masterclass. Today, we are going to bridge the gap between abstract mathematical theory and practical machine learning code, demystifying the complete evolution of tree-based models. Let's start with a fundamental problem. Imagine a complex, nonlinear dataset. If you try to fit a standard linear model, like logistic regression, you are forcing a rigid, straight line through a problem that requires flexibility. A decision tree completely abandons the idea of a single global equation. Instead, it recursively slices the feature space into orthogonal rectangles. It asks a series of simple yes or no questions, creating a stepwise decision boundary that perfectly isolates the complex patterns. But how does the tree mathematically know exactly where to make these orthogonal slices? That brings us to impurity metrics. At the heart of every decision tree is a mathematical quest for purity. The algorithm evaluates every possible feature and every possible threshold, searching for the split that maximally separates the classes. The default metric in Scikit-Learn is Gini Impurity. It represents the probability of incorrectly classifying a randomly chosen element in the dataset. If a node is perfectly pure, the probability of a misclassification drops to 0, and the Gini impurity is exactly 0. Alternatively, you can use entropy, rooted in information theory. It measures the amount of chaos or disorder in the node. While mathematically different, using base 2 logarithms instead of squared probabilities, it achieves a very similar result. In practice, Gini is computationally faster. Once the impurity of a potential split is calculated, the tree measures the information gain. It mathematically subtracts the weighted average impurity of the resulting child nodes from the impurity of the parent node. The split with the highest information gain wins. Watch what happens as the tree searches for a split. Before the split, the dataset is a chaotic mix. Our probability bars show a 50-50 split of classes, and the impurity is high. When it finds the optimal threshold, it splits the data. The resulting child nodes are perfectly pure. The probability bars snap to 100%, the impurity meter instantly drops to 0, maximizing our information gain. But what if we aren't predicting a class, but a continuous number? That's where regression trees come in. Instead of measuring class purity with Gini, we measure variance using mean squared error. The tree tries to find the split that minimizes the variance of the numbers inside the leaf. When a new data point falls into a leaf, the tree doesn't predict a class. It predicts the average value of all the training points in that leaf, creating a step function boundary. A decision tree's greatest strength is also its fatal flaw. If left unconstrained, a tree will aggressively grow until every single leaf is perfectly pure. This results in incredibly deep trees with highly jagged, complex decision boundaries. This is a textbook case of overfitting. The model has memorized the statistical noise in the training data, and its performance on unseen test data will be disastrous. To fix this, we use pruning. There are two main strategies. The first is pre-pruning. By hyperparameter tuning the max depth or setting a min samples leaf threshold, we artificially force the tree to stop growing early. The second, mathematically rigorous strategy is post-pruning, specifically minimal cost complexity pruning. We let the tree grow fully, but then we introduce an alpha penalty into the objective function. The alpha parameter penalizes the absolute size of the tree, denoted by t. The algorithm selectively snips off weak branches, collapsing them back into parent leaves, until the tree reaches the perfect balance of bias and variance. But even with perfect pruning, a single tree is fundamentally unstable. Small changes in the training data can cause massive shifts in the structure. That's why we rarely use single trees in production. To solve the instability of single trees, we move to ensemble methods. The most famous is the random forest, which relies on a technique called bagging, short for bootstrap aggregating. Bootstrapping is a statistical resampling technique. Instead of training one tree on the entire dataset, we create many subsets by randomly sampling the original data with replacement. Because we sample with replacement, some data points are repeated, and roughly 37% of the original points are left out entirely. These are called out-of-bag samples, and they act as a built-in validation set. But random forests add a second layer of randomness. Feature bagging. At every single split, the tree is only allowed to consider a random subset of the features. This brilliant constraint actively prevents the trees from becoming highly correlated. Finally, we hit the aggregation phase. We have trained hundreds of deep, uncorrelated trees in parallel. When a new data point arrives, every tree casts a vote, and the forest outputs the democratic consensus. The result is a massive reduction in variance with almost no increase in bias. If bagging is about independent parallel voting to reduce variance, boosting is about sequential learning to reduce bias. It's a completely different philosophy. It all started with XGBoost. XGBoost trains a very weak model, often just a decision stump with a depth of 1. It looks at the predictions and identifies which data points were misclassified. Then, it explicitly increases the sample weights of those specific errors. Visually, you can think of the misclassified points becoming larger and heavier. The next tree in the sequence is forced to prioritize these difficult points. XGBoost was brilliant, but gradient boosting completely generalized the math. Instead of hacking the sample weights, gradient boosting treats the problem as numerical optimization in functional space. If our true data is a continuous curve, and our first tree is a simple step function, there is a leftover error between the prediction and the truth. These leftover errors are mathematically the negative gradient of the loss function, known as pseudo-residuals. The next tree doesn't try to predict the target variable at all. It trains directly on these residual arrows, pointing down the gradient to correct the exact mistakes of the previous tree. Gradient boosting provided the perfect mathematical foundation, but standard implementations were notoriously slow. This paved the way for the modern titans of tabular data, XGBoost and LightGBM. XGBoost, or extreme gradient boosting, dominated Kaggle competitions by pushing the math to the absolute limit. Standard gradient boosting only uses the first derivative, taking blind steps down the gradient. XGBoost explicitly optimizes a heavily regularized objective function. It calculates the loss over the previous predictions plus the new tree's prediction, but it adds an omega penalty term. This omega term strictly penalizes the number of leaves and the leaf weights, building extremely robust trees that strongly resist overfitting. Furthermore, to optimize this quickly, it uses a second-order Taylor expansion. It calculates not just the gradient, g, but also the Hessian, h, the second derivative. This provides curvature information, allowing XGBoost to take a massive Newton-Raphson step directly to the minimum. Then came LightGBM from Microsoft. It completely changed the algorithmic growth structure. Let's look at the difference. XGBoost grows trees level-wise, expanding all nodes at the current depth simultaneously. XGBoost expands layer by layer, keeping the tree perfectly balanced, but potentially wasting computations on low-gain splits. LightGBM introduced best-first, leaf-wise growth. It aggressively searches the entire frontier and splits only the single node with the highest potential variance reduction. This creates asymmetrical, incredibly deep trees. Combined with histogram-based binning, LightGBM is the undisputed king of training on massive datasets at lightning speed. All of this theory means nothing if we cannot deploy it. Let's look at the actual Python code implementations, starting with Scikit-Learn. In Scikit-Learn, moving from a single highly variant decision tree to a robust random forest is as simple as swapping the class. Notice how we specify the impurity criterion and max depth for the single tree, but for the forest, we define the number of estimators and the feature bagging constraint. When we move to the advanced titans, XGBoost and LightGBM, the syntax shifts to highly optimized C++ wrappers. In XGBoost, we wrap our data in a D-matrix object. We define the objective function, And crucially, we set max depth to control its level-wise, symmetric growth. LightGBM uses a similar API, but look at the parameters. Instead of max depth, we explicitly define num leaves to control its aggressive, asymmetric leafwise expansion. One of the greatest advantages of tree-based models over neural networks is their extreme interpretability. Because they split on features directly to maximize information gain, we can dynamically calculate feature importance during training. As the model trains, it tracks every split. We immediately see that income provided the highest Gini reduction, making it the most important feature, followed by debt, and finally age. From the humble, single decision stump making simple binary splits, to the massive, Hessian-optimized mathematical engines of extreme gradient boosting, you have now mastered the evolution of tabular machine learning. While deep learning completely dominates unstructured data like images and text, tree-based ensembles remain the absolute undisputed champions of tabular data. They are faster, highly interpretable, and mathematically robust. Thank you for watching, and keep building.